Okay, so very good afternoon, all of you, and we welcome you all in this third day of lecture series on brain behavioral AI with the epitome of AI. So we are honored to have Professor Suresh Devasahayam sir with us. So it is means we are having a privilege to have him on today's session, and definitely we are going to have a very insightful session. A short words about Suresh sir is that he is currently working as an independent researcher to develop a device for neurotrauma and special injury assessment. He is on extraordinary leave from IIT Jammu, where he is a professor of electrical engineering. He was professor of bioengineering at Christian Medical College, Vellore, till 2021. That was the age of retiring of 60. Before that, he was an associate professor as the IIT Bombay till 2022 in the School of Biomedical Engineering, which is called as a Department of Bioscience and Bioengineering. He obtained his PhD and MS degree in bioengineering from the University of Illinois at Chicago, with his BE in electronics and communication engineering from the College of Engineering, University of Madras. After postdoctoral research in neuroscience at the University of Alberta, he joined IIT Bombay in 1990. His research interests are in medical instrumentations, biomedical signal processing, physiological system modeling, physiological measurements, and neuromuscular assessment. He has developed and transferred technologies for psychological measurements and signal analysis. He has taught courses of electronics design, control system, signal processing, physiological system modeling, etc. His book, Signals and Systems in Biomedical Engineering, published by Springer Matured, is among his contribution to teaching the subject, and the third edition was published in 2019. He sits on various technical committees and serves in administrative roles. So this is what is the profile of sir, but in person, what we understand with the use lots of guidance of sir. He is a true mentor of us. He supports us in all the direction, and he is so polite and humble. He sits with us and he make us understand so many nuances of the technology, and he's supporting us a lot in guiding us a lot in our current ongoing projects. So this is what I can say about sir. Thank you, sir, for accepting our invitation, and we welcome you for this session. And we are looking forward to hear from you, sir.
Thank you, Dr. Priyanka, and thank you for all the kind words. At the beginning, let me say that I have a bit of a sore throat for the last few days, so I might need to take half a minute break occasionally. In discussions with many people in the group at CDAC Delhi, I felt that talking about some signal processing methods is a good review that many people might enjoy. I hope you do. So that's why I said I'll talk about essential signal processing for brain-machine interfaces.
Essentially, that is very much required, sir. The means we are starting, it is a very much required subject for all of us to learn, sir.
Good. So I hope at the end of the session you find that it has been useful. So here is an overview. So I thought I'd first talk about brain-machine interfacing. Because brain-machine interfacing is a little different from other applications in biomedical engineering or signal processing. So a few words there, and then a little bit about hardware and algorithms. And I'll show some aspects of hardware in my discussion, and then say why signal processing is important. And when we talk about signal processing, the classical way of looking at it is to look at time and frequency domains. I had a meeting with a friend in IIT Bombay yesterday, and the same thing came up as to how sometimes people say, can we stick to only one of the domains and not look at both? I think it is useful to look at both, and a lot of things that we do benefits from looking at both the time and frequency domains. Then analog and digital signal processing are both important, and I'll touch on both of them. Of course, the emphasis will be on digital signal processing. And what I will try to do is to demonstrate some of these techniques. And a key aspect of signal processing is filtering. Again, I will try to demonstrate some aspects of filtering. And Then I'll say a little bit about feature extraction and then I'll conclude. So, an overview of brain-machine interfaces. So, brain-machine interface is also called human-computer interface. So, these two terms should be used interchangeably. And definitions, of course, vary slightly from place to place. In the next slide, I'll say a little bit about the full aspect of brain-machine interface. Now, the user needs have to be assessed. So when we usually talk about brain machine interfaces for people who have some reduced capability to interact with their environment. Although nowadays we are talking about brain machine interfaces also for people with full normal capabilities of human beings. So a mouse, for example, a computer mouse or a trackball is also a brain machine interface. A gesture recognition system like a touchpad and so on is also a brain machine interface. They are all used by people with neurotypical or normal capabilities. But in the case of people with disabilities, it becomes very important to know what exactly are their needs. Do they need to be able to speak? Do they need to be able to ask for certain assistance? Do they need to be able to operate their wheelchair, their mobility device, and so on? And then we also need to assess their capabilities. Can they move parts of their body? Can they speak? So, what is it that they are able and what is it that they are unable to do? And uh, an important aspect of this is whether they have normal cognition. Now, when I say normal cognition, I give a very simple example. Let us say there is a person sitting in a wheelchair and the person needs to navigate the wheelchair. It seems like a simple thing to do. So the normal way you would navigate a wheelchair, I'm talking about electric wheelchairs, of course. A motorized electric wheelchair would be navigated with a joystick. So you push it forward, goes forward. You pull it back, it brakes, and then you pull it more back, it stops. Left turn, right turn, and so on. Now imagine that the person is on a corridor, like we see in many of our buildings, and the corridor does not have any guardrail. Now, and also imagine that this person has limited cognition. The person is not able to see very well, is not able to turn his or her head very fast, is not able to hear people very well. And so now, under very special conditions, this person will be able to navigate this corridor. But suppose there is suddenly somebody rushing by and the person actually turns and falls off the edge of the corridor. Now, this can happen off the edge of a corridor, it can happen in a staircase, and so on. Now, so we are not talking about people with very good abilities like a normal human being, but somebody with limited abilities. And this is something we have to keep in mind because safety is the most important. Then what kind of movement do they have? So when I have worked with the Rehabilitation Institute in CMC Vellore, we used to have people who have had strokes and therefore were able to see, understand, but could not speak. They also could not move their hands, but sometimes they would have a little bit of movement in their finger. They might have movement in their leg. They might have head movement. Uh, in very extreme cases, they would not be able to move anything other than their eyelid. So, what is the movement that they have? And we should see if we can harness that. And what is the sensory awareness? Like, can they see well? Can they hear well? And all that. Then how do we obtain the signal? So if suppose there is a person who can only move his or her eyelid, can you pick up the eyelid movement using a sensor? Yes, there are many different ways of picking up eyelid movement. Interestingly, one method is an electrical method. Other methods are mechanical methods. So these have been used. The So I'll say a little bit more about this in the next couple of slides. Another method of obtaining user signal, which is very common, is to look at electrophysiological signals. When we say electrophysiological signals, we are looking at electroencephalogram that is picked up from the brain by placing electrodes on the scalp, electromyograms, which is picked up from the muscles by placing electrodes on the skin over the muscles, and so on. To be complete, I should also say there are signals like electrooculogram, electroneurogram, all of which can be picked up without too much difficulty. And then you have to decode the user intention. So suppose I say that there is a person whose only capability is to move the eyelid, but the person is able to understand everything that is going on around him or her. Now, if this person wants to ask, please give me some water. Now, if the person is only able to blink eyelids and you're able to pick it up, now you're all familiar with the idea of a Morse code. So you can use the eyelids to generate something like a Morse code. Now, in digital technology, we would call it a way of converting serial data into parallel data. And that is what I mean by decoding user intentions. And there are many different techniques that are used for this, for getting the user intentions, whether he or she wants water, whether he or she wants a right text in an email, and so on. And then you've got to transfer the user intentions to the target. So the target may be, again, let us say, uh, maybe a robotic device that brings a glass of water to the person, or an alarm that calls the attention of a helper and so on. Or it may be something that connects to a computer to accept a character input for typing an email. So this is what we mean by BMI. There is one more aspect which I will show in this picture. So here I have a picture. When I say user intention, intention is always generated in the brain. And this intention we obtain using different kinds of sensors, as I already mentioned now. And this information we have to process using analog processing. Then we digitize. Sorry. Because we digitize, because all machines nowadays, I think almost universally, are digital machines. And the physical movements are continuous time or continuous analog signals. So we have to convert these uh, analog signals into digital signals using a digitization process. And then we do all the processing using digital machines. And then we give it to the external action, which is put it into an algorithm, give it into a text input to a computer, give it to a switch that will turn on the lights, that will turn on the fan, and so on. Now, sometimes the user also wants to be aware of the environment. So, for example, if I'm sitting in a chair and I'm unable to turn around, and every time somebody comes into the room, I want to be aware of. Now, I can do something very simple like put a mirror in front of me. But suppose I'm also having some visual impairment. Then it will be nice if I can have some way of alerting me that somebody is coming in. So the feedback or information about the environment being presented to the user is also part of a complete brain-machine interface. Okay, I'm not going to say very much about this, but just as an example, now you might have heard of artificial limbs being used. Artificial hands, for example, form a very important part of services for disabled people. So if you have an artificial hand and you're using this artificial hand to perform various tasks. Now, so if you want the hand to open, close, the brain-machine interface gets the intention from the brain of the user, converts it to the opening of the hand by motors, closing of the hand by motors, and so on. Now, suppose you're picking up, let us say, a cup. And the cup is either, let's say it's a paper cup. It's a simple example. It's a paper cup. And the paper cup is either full of water or empty. Now, when I pick it up and lift it, if it is empty and I give it too much force for raising, I might end up spilling it. So I need to have some information about the weight of the cup given back to my body. Although I'm apart from my amputated hand, everything else is normal to me. So this information is important to be given back to the user. Now, more crucially, suppose I'm picking up this cup of water. If the cup starts to slip, can I get information about the slipping of the cup and give it back to the user? As you can see, all these are part of brain-machine interfaces. And I have brought in this idea of signal processing by saying we need to have analog processing, digitization, numerical processing. So when we say brain-machine interface, hardware, algorithms, I can, let's uh, make it a little more interactive. And I'll give you an example of mechanical sensors that can be used for picking up movement. So what I'll do is, let me minimize. what I'm going to show is, see, I have here a accelerometer. I'm going to show it very close to the camera. So I hope you can see it somewhat. It will not, my camera will not focus. And because I don't have a magnifier, so this is a printed circuit board in which there is a small chip in the middle, and the size of the chip is 4 millimeter by 4 millimeter. And on the board itself, there are two lines drawn saying this upward is the y direction, left to right is the x direction, and front to back is the z direction. So I have connected this to some hardware. First, let me demonstrate. You can see on my screen, there are three traces being seen, right? So these three traces show the x acceleration, the y acceleration, and the z acceleration. Let me show that I can pick up the motion in the x direction. So suppose my head is, oops, sorry. I have a cable issue here. Make a violent movement, one cable becomes loose. So let me again show. So if I make up and down movement, can you see that only the top trace moves up and down? If I make a left to right movement, only the second trace moves. I'm not doing an exact left to right without an up and down. But if I do a front to back, you'll see only the third trace move, right? The other two, because I'm not doing exactly in the direction. Now, if I place this on my head and I do this, or I do this, or I do up and down, I can separate these three movements and use them as part of a brain-machine interface. I can also make a smaller board and place this on maybe my eyelid, maybe my cheek, and when and use it for picking up cheek movement. Maybe if I have only a finger movement, I can use it to pick up my finger movement. Yes. So all these are possible. Now, as you can see, when I make this movement, there is this gross movement which you can see is associated with the movement of my hand. Now, there is some very rapid movement that sometimes comes, right? So that is what I will call noise. And to avoid that noise, can you see there is a little box that pops up, and I can adjust the sensitivity. So now the sensitivity is, let me increase the sensitivity. I'm increasing the sensitivity, but that is not the point. I want to change the filtering. So I'm changing the filtering just for the sake of demonstration. I've changed it by a rather large amount. Now, when I move it, you will see no rapid movement in the top channel. I've only changed it for the x-axis. Okay. So if you see here you see these sharp movements, but in the x-axis there is no sharp movement. So if you want to ask any questions when I'm with the hardware here, please ask me. Otherwise, I will continue with the rest of the. Okay. It's much better when this is done live. I mean, in person. I mean, this is live, but it's in person.
Hello,
Okay.
sir.
There are no. Yes, please.
Sir, what is the name of the sensor?
The
Please do it.
sensor, the chip itself is called MPU 9250.
Okay, sir.
Okay. The chip has a 3-axis accelerometer for X, Y, and Z direction. It also has a 3-axis gyroscope. So if you like, maybe if we have time at the end, I can show you. The gyroscope also can be picked up. The gyroscope measures angular velocity. So it is very useful for doing rotation only of the head. It also has 3-axis magnetometer. So if you want to measure movement with respect to a magnet that is placed close by, the magnetometer can be used. It also has a temperature sensor. So it actually has 10 sensors built into this 4 millimeter by 4 millimeter by 1 millimeter size chip. Any other questions? So I showed the acceleration, angular rotation sensors. Similarly, there are force sensors. So if you want to pick up the force of gripping with your hand, that is also used sometimes for brain-machine interface. Now, picking up electrophysiological signals, I want to illustrate something here. So let me again go to a so here I'm not going to do a real signal. I'm going to use a simulated signal to explain. So what I want to explain is you usually pick up an electrophysiological signal by placing electrodes in the vicinity of an electrically active part of the body. So if you're placing the electrodes near the brain, you will pick up signals generated in the brain. If you place the electrodes near the heart, you will pick up signals generated by the heart, from the muscles, and so on. The technique is essentially the same. You are placing two electrodes that pick up the potential generated by the electric field generated by the electrically active part of the body. So let's look at this. Okay. So here I have a simulation, and what I want to highlight here is there are two electrodes, and I can change the distance between the electrodes. Can you see? The spacing between the electrodes changes. Now, each of the electrodes, so one electrode I've called electrode A and electrode B, and I'm showing the electrical potential picked up by electrode A and electrode B. Anybody wants to ask me an instrumentation question, please ask, but otherwise I will just mention it and keep going.
Sir, one basic question. When we are saying that EA is providing the signal from electrode A and electrode B, I think there should be some reference and base signal.
Correct. Exactly. So the reference is an electrically inactive part of the body. So the circuit ground of the amplifier will be connected to what will be called a ground electrode or reference electrode. And so, okay? So in this case, you can simply place it on somewhere in the back or on the stomach, anywhere that is electrically inactive for this purpose. Now, electrode A and electrode B are picking up signals, and to make it realistic, I have a power line noise source here. So this power line noise source is resulting in a very large 50 hertz noise, which is sinusoidal, appearing in both these signals. And as you can see, it's very large.
Can I interrupt?
Yes, please.
Thank you. Thank you. Actually,
Yes.
because you are talking about hardware, it's easy for us to relate.
Yes.
Because partly we also have brain. That's one. I mean, we can relate to brain.
Yes.
Second is this so-called sensors, or you can even add actuators, whatever that is. Real world, we can see that.
Yes.
So this input output are understood, and something in between called brain is also sort of we can relate to it. It's not too abstract. Like in the AI and other things, we don't even know what's going on in DLL, for instance. So I have put a questions in the chat box.
Okay, I'm just seeing that.
Just have a look at it. Where are we picking up the analog signals from? Is my first question.
Now, as I said, if you're interested in brain signals, what we call electroencephalograms, you would pick it up by placing them on the scalp. You just place two metal discs on the scalp, and to make the conductivity between the metal disc and the tissue underneath better, you use what is called electrode gel. So people talk about tri-electrodes, but essentially the point is you're going to place the electrodes on the scalp. If you place electrodes on the chest, you're going to pick up the signals mainly from the heart. Why does it not pick up signals from the brain? It does pick up signals from the brain, but the signals from the brain will be very much smaller, about 1,000 times smaller than if you place it close to the brain itself. Now, the signals from the brain in general are rather small for various reasons. I'll give some examples of that a little later. They are on the order of a few microvolts. The signals from the heart are somewhat larger. It's on the order of hundreds of microvolts. Therefore, if you place it as far away from the heart and muscles on the scalp, you're going to pick up brain potentials best. If you place it near the heart, if you place it near the hand muscle, my biceps, you will pick up muscle potentials best. So this is how we are picking it up, essentially by placing electrodes. As I said, when my brain is electrically active, it generates a potential, an electric field. So there is going to be a positive side and a negative side, and there's an electric field from the positive to the negative. Now you place a pair of electrodes or wires in the path of this electric field. You will find that what you're doing is electric field multiplied by the distance between your electrodes is what you pick up as an electrical potential. And that potential is continuously changing in time. And that is what we mean by a signal.
Thank you.
Okay.
So I
Now,
think second question is bypass because you already answered it.
no, let me answer that also. Because when I am sitting here fully awake, I don't want the electrodes to be placed under my skin. But there are situations when I might be unconscious for some reason. And the team that is taking care of me might want a very good signal that does not get attenuated by the insulating properties of the epidermis of my skin. And therefore, they will find it useful to place electrodes under my skin. So they just put needles and insert it under the skin. Same thing can be done for muscles. It's also done in the heart when they put a catheter into the heart and you have electrodes there. So
What
the
is
closer
that?
you can
What
get,
is the voltage and what is the safety factor?
so there is no say, you're not applying anything. You're only picking up the field that is generated by the body potentials.
I see. Okay. So
Okay.
what is it order of magnitude that is? Is it millivolts or microvolts or?
So in the case of the brain, it's microvolts. In the case of the heart, it's about hundreds of microvolts.
But
and
there is no safety problem.
there's no safety. Since you're saying that you're happy with the hardware, when you use an amplifier, an operational amplifier, there is what is called bias currents, which means currents flow in and out of the terminals. So now this is not desirable. So what we would like to have is FET input stages. And if you have field effect transistor input stages, then you really don't need to have any significant current. You can have, theoretically, you can have picoamperes of current flowing for the measurement for the FET to be activated. So there is no safety issue. But if you use something like a very cheap operational amplifier and you're going to place the electrodes, let's say in a catheter inside the heart, then definitely there is a problem.
Then as per the
because of-
equation you
Yes.
wrote, once
Yes.
you start going down and then pico amplifier,
Yes.
your noise component compared to signal increases. Your CNR or SNR, if you look at it,
Yeah.
as you go down the pico amplifier kind of a level, will that not be a bit of a problem?
Yes, I mean, they are not always coupled or they're not always linked. In the sense, if I say I'm interested in a microvolt signal, and one problem is my connection between my source and my measuring device is a very high impedance connection. Obviously, you don't want to use a wire that has 10 mega ohms of resistance, right? Now, the epidermis of the skin is one such high impedance connection. So by getting under the skin, you are reducing the impedance of the contact.
Okay.
And therefore, you are prioritizing the signal from the body and deprioritizing the signal that is coming from outside.
Okay.
I'm assuming the noise you're talking about is 50 hertz noise that is coming from the surroundings. That is the
external sources.
external noise. Electronic noise is something else.
Okay, got it. Last question.
Yes.
It is written there. What is the terminological definition of the entity called brain? Because whole topic is all about brain-computer interface.
Yes,
I
sir.
want to know, see, I am now dealing with systems, subsystems, components, and
Yeah.
I'm all dealing with standards where for one of the every standard, first item is terminologies, definitions.
Sir, Ramki sir, just a minute, sir. I'll just interrupt in between. Suresh sir, I'll just would like to introduce Ramki sir to you. Sir
Okay.
has been DG of CDAC, and he is looking
Okay.
after a lot many national impactful projects, and he is
How nice.
sir. So he is
Thank
mentoring
you.
us for doing standardization projects, accessibility, and whatnot. So
Right.
he is one of
Right.
the person who made us capable enough to understand all those concepts, and
Excellent.
he guided us all through years, sir. So this
I'm
is just
very
a brief
happy to know.
introduction of Ramki sir.
Thank you.
Sir, please go ahead, sir.
So what I wanted to know is, I mean, I'm now asking from a very much common man point of view. This word
I think
the brain
yeah.
is used so loosely or understood so loosely. Please
Yes.
demystify it to us.
Okay. Excuse me. So, if I understand your question correctly, I'll put it like this. There are parts of the brain here and here that is right on top of my head and a little bit to the back, which is called the motor cortex. So now if I say I want to move my right hand forward, then it starts by electrical signals being generated in parts of the brain deep inside. That is, it's closer to the top of my mouth, inside my mouth, rather than to the outside. It starts there, and then it goes to the left side of my brain because I'm going to move my right hand, and then it causes electrical signals in the motor cortex. If I want to pick up a signal very specifically from the motor cortex that is responsible for moving my thumb, theoretically it's possible because I would have to place the electrodes close to a certain part of my brain here. And for exact location, there are various techniques. Now, is it technically possible today to do it without breaking the skin? No. Is it at all possible? Yes, because during surgery, sometimes a surgeon has to remove a part of the brain. It might be a tumor or something else that causes a problem. Now, along the way, they don't want to damage certain crucial parts. So they would like to know whether this relates to the right hand and thumb and the forefinger because they want to spare them. Now, what they can do is during surgery, they can place very tiny electrodes and stimulate that part of the brain and see if the right thumb is moving. If it is moving, they'll say this is the part of the motor cortex that is responsible for the right thumb and we will not touch it. So this way, there are functions known for various parts of the brain. I hope I have answered your question.
Yeah. Thank you so much. Eminently, I could understand that. Thank you so much.
Well,
I will not interrupt again. Thank you.
that's up to all of you who are organizing. I'm happy to answer any question. Let me start this. Please. Okay. So now, usually because of this noise from outside, the most common way of measuring is what is called bipolar measurement. That means we take the potential from electrode A and the potential from electrode B and take the difference between them. So this is a differential amplifier and then we use it. So what is seen at the bottom is the signal that is the difference of electrode A and B. As you can see, the noise is more or less cancelled out. Now, if I increase the spacing between the electrodes, then the potential at A is much more different from the potential at B. And therefore, the subtraction does not give us an exact, very good subtraction. If I keep them very close together, then you can see the subtraction gets better and excitation. That means there is a signal in the somewhere here.
Sir, a basic question. whether these
Yes.
two electrode A and electrode B are having the same phase and same sine waves or cos waves, or means if there
So,
any difference between the frequency and voltage, or same frequency and same voltage.
so the sine wave that we are seeing is the noise from 50 hertz. So these are 50 hertz noise, sine waves. So electrode A is picking up 50 hertz from the mains, and so some wire may be running nearby and picking up 50 hertz from that. Electrode B is also picking it up. Now, if you keep them very close to each other, then they are picking up the identical signal, and therefore subtraction can be very good. So
Yes.
here I have generated a biological signal. So I'll do it again. So as the generated biological signal, if I look at the potential in A and B, you can see that the biological signal has caused some kind of disturbance, but it is not very clear. But if you look at the difference between A and B, you see a reasonably good signal, but it's not good enough. The 50 hertz noise still persists. So what can we do? Let's try improving what is called the CMRR. And as you can see, CMRR can get worse, but this is about as good as it gets, I think, with just CMRR. Now I can add a notch filter. And when I add the notch filter, then you can see that the 50 hertz is completely removed. So what is a notch filter? A notch filter is a filter that removes exactly the frequency that that we want to discard. And in this case, it's a 50 hertz notch filter. Now let me again cause the excitation. As you can see, we see a very clean signal. So this is the importance of a notch filter. And here, this notch filter is a physical filter or an analog filter. Okay. Now let me go back to the slides. Okay. Now, why signal processing? I hope I have at least illustrated the importance of using analog filtering. And we often also need to use what are called anti-aliasing low-pass filtering before digitization. Again, we'll show this with an illustration. And after we do the digitization, we have to do a lot of digital signal processing. And we can also use filtering digitally. So we can apply a notch filter with a digital filter also. Then why would we want to use analog filtering if we can do everything digitally? Because it seems to be cheaper and much more flexible to do digital filtering rather than analog filtering. The very simple answer is sometimes if your noise is large and your signal is very small, you want to magnify your signal so that you have enough resolution or enough number of bits to represent your signal. Now, if you're unable to amplify it enough because the noise plus the signal is so large that you cannot amplify it very much. Because if you saturate the digitizer, then you're going to lose some information that will be part of the signal itself. Therefore, we should get rid of the noise as much as possible before we digitize. And what remains, we may want to use digital filters. Okay. And we often, when we talk about filters, when I say we want to use a 50 hertz filter, when we say 50 hertz, it is a frequency terminology that we are using. And therefore, we are used to thinking in terms of time and frequency. But when we bring in the algebra and algorithm, sometimes people worry about time and frequency domains. So let me go through that quickly. Feature extraction can be done in the time domain and in the frequency domain. And there are advantages and disadvantages in both. So when we say time and frequency domains, very simply, you can describe a time domain signal with time as the independent variable in terms of its frequency components or the amount of energy it has in different frequencies. And this is the Fourier transform. we can calculate the so-called Fourier transform using this formula. And from the Fourier transform, we can go back to the original time signal. So the Fourier transform is a technique by which we can go back and forth. Again, this is just a review, I think, for most. So let me do a demonstration of this. Okay, I hope you can see this. And what I have got here is a simulation of the EEG. Okay. Now you might say that it is very bold of me to say that I can simulate the EEG, because have I really simulated the brain? No, I have not. The EEG can be modeled, or at least one channel of EEG can be modeled as a pseudo-random process. So what I have done, I will put some of the mathematics at the end, is made an autoregressive model with a few parameters, and the residue is a random noise. Okay. So the upper trace shows the EEG. Now, as you are aware, when you put on EEG electrodes and amplified and see it on screen, yes, if the subject is very relaxed, you see what are called the alpha waves very prominently. And if the subject is alert, then the rhythmicity of the alpha waves is lost and it becomes much more non-periodic. So here I have something called alertness factor, and I can increase or decrease the alertness. So if I increase alertness, the signal changes. But if you look at only the upper trace, change is not obvious. It does not, it looks like something that is randomly going up and down, whether alertness is low or high. But in the bottom graph, what I have got is the frequency decomposition. The horizontal axis is the frequency axis. The vertical axis is the power in each of these, all these frequencies. The range of the horizontal axis is 64 hertz. I don't know if you can see it. Might have moved this. You can see it, 64 hertz. So each of the major divisions is about 8 hertz. So when alertness is low, you can see that a lot of activity is around 8 hertz. Right? 8 hertz, sometimes around 10 hertz, 12 hertz. All these are what are called the alpha wave band. Now, if I increase alertness, it spreads out. Can you see? Let me increase the gain. You can see it is very spread out. So there's a lot more activity in other components. There is no single frequency that you can call alpha. Let me again reduce alertness. So you can see in this band of 8 hertz to 12 hertz, it has gone up quite a lot. And so with low alertness, that means when I am relaxed, calm, almost falling asleep, you will see a lot of activity in the 8 hertz to 12 hertz band, which we call the alpha wave. So now it's all very well to say that you can decompose it like that. So let me give a sine wave, and I hope it is useful in illustrating the concept of the Fourier transform. So now I'm going to generate a pure sine wave. So what I'm doing is called the short-time Fourier transform. It is a digital or discrete Fourier transform technique. And as the signal is changing continuously, I am taking it, calculating the Fourier transform, averaging a few blocks and drawing it at the bottom. So now I have a sine wave of 12.5 hertz. So I have a peak at 12.5 hertz. I also have a few side lobes that are around 12.5 hertz. Okay, I'll just mention a little bit about it along the way. When I increase the frequency, can you see the time domain? You can see the frequency is becoming higher. And as you can see, when I stop, when I stop changing the frequency, now it takes on this new value of 20.4 hertz. So you can see the side lobes are changing up and down. Now, if I don't use what is called a window, the side lobes become much more prominent. To reduce the effect of a window, I will use different types of windows. Here you can see there is no side lobe, but the main lobe itself has become broader. So this is the concept of using windows for power spectrum estimation. The use of windows removes these side lobes because the side lobes cause confusion. Are there actually frequencies in those side lobes? When I use a window, which is, I've used a Bartlett window, I have a Hamming window, Bartlett window, and Blackman window. They are all slightly different depending on your applications. They trade off between keeping a little bit of power in the side lobes and or having a broad main lobe itself. Okay. So this is the idea of the Fourier transform. So if I have a pure sine wave, then I have only a single frequency. You can see I've changed the frequency again. It's a single frequency. There are various issues in the calculation of the discrete Fourier transform, which is actually being manifest here when you see it jumping all the time. But I'm not going to go into that unless somebody has a question. Okay. Now, I said that I'll also talk about the importance of conversion from analog to digital. How are we doing? We're not doing very well for time, no? So I'm going to skip this, if you don't mind.
If everyone is okay, I think we are good to go, sir. We would like to learn because time is not a very much constraint. I think we should take this part along, sir. We
Okay.
should get it, sir.
Okay, let me then do a simulation of this.
Sir, I have
Yes,
one
please.
question.
Please,
Sir,
yes.
how can we decide that which window will we use for the decreasing the side lobes?
So as I showed in that simulation, the Bartlett window and the Blackman window are better at suppressing the side lobe, but they will give you a broader main lobe. The Hamming window is the most commonly used window because
Yes, sir.
occasionally it will give you very small side lobes. But its main lobe is also as narrow among all the windows. There is also another window commonly used called the Hahn window, sometimes erroneously called the Hanning window. It's actually the Hahn window. I think
Yes, sir.
Oppenheim and Schaefer made that mistake in their 75 edition or something, and afterwards it has been called Hahn window. So the Hamming window, the Hahn window, Blackman, Bartlett, these are the common windows.
Okay, sir.
I would suggest going with the Hamming. That's good enough.
Yes, sir. Okay, thank you, sir.
Okay. So here I have what I wanted to mention in the slide is that in the top graph here I have an analog signal. Consider it an analog signal. And in the middle, I have the digitized version of it. So the middle is drawn. Let me draw it with a very low resolution. Okay. So if I pause, you can see I'm drawing the analog signal on a graph paper with horizontal lines and vertical lines. Now the vertical lines represent the time interval at which I will take samples. The horizontal lines represent the number of digital values that I'm going to convert. So if I have 3 bits, then I have 000, 001, and so on up to 111. So I have 8 levels. So there are 8 levels of horizontal lines, and the vertical lines with 8 hertz of sampling are going to be 16 and 2 seconds. So the entire width of the graph is 2 seconds of data. Now, so the last window shows the reconstructed version of the digitized signal. So here, if I have a 6.5 hertz sine wave and I have sampled it with a frequency of 8 hertz or 8 samples per second, and I try to get back the original signal, I am not going to be able to do it. I end up with what is called aliasing. Let me illustrate this. So if I increase the quantization level, so it is aliased, I can use different techniques for for connecting the points. And I have here only zero order hold and linear interpolation. Technically, what is best is uh, a, a very good quality low pass filter. But my point is to say my 6.5 hertz input signal, analog signal, is now appearing as a 2.5 hertz signal when I try to reconstruct. This is what we call aliasing. Now, why is so? The 6.5 hertz is now appearing as something else, or it is appearing as an alias, like all our villains in our movies. It is appearing as something else. So that is why it is called aliasing. So let me illustrate it again. On the left side, sorry, on the right side, I have, can you see it? I have a couple of graphs. The two graphs are the Fourier transform of the analog signal and the discrete time Fourier transform of the digitized signal. Now, what happens when I digitize? Are you able to see it clearly? So let me digitize like this. So I'm digitizing 64 hertz. This is the sine wave. So you can see, just like I showed with the Fourier transform simulation earlier, when I change the frequency, my Fourier transform here is changing, right? Now, what is happening in the discrete time Fourier transform? The discrete time Fourier transform results in a repetition of the continuous time Fourier transform with an interval of equal to the sampling frequency. That means this green rectangle that I've drawn depends on the sampling frequency that I use. The smaller the sampling frequency, the narrower is that rectangle. The higher the sampling frequency, the bigger is that rectangle, because, as I said, that is the block that is being repeated. As you can see, whatever is inside this is going to be repeated. So I don't have to have only a pure sine wave. I have also got simulations of the iotic waveform or the ECG waveform. So these are ECG waveform. So whatever is within this rectangle is going to be repeated. And that is a phenomenon resulting from the discretization of the signal. It is only because of the discretization. Now, assume that I have this ECG signal. It's a good way of illustrating it. And I reduce the sampling rate. As you can see, this block, when it repeats with this interval of the green rectangle, it is merging with the next repetition bit. And therefore, it is now resulting in this interference, which means whatever you do, you cannot get back this original waveform of the Fourier transform. Let's go to an even worse sampling rate. Can you see from this little squiggly waveform, you can never get back this original Fourier transform. But if I have a high enough sampling rate, by simply cutting off everything outside the green rectangle, I will be able to recover the original signal completely. But what is the method for cutting out everything outside the green rectangle? Is a method for algorithms and all of that. But mathematically, it is possible. That's all I want to say here. If you have any questions, please ask. So very often, I have a
Sir,
simulation. Go ahead.
hello. Sir, my name is Abhijit. Sir, what is the significance of this discrete time Fourier transform? Like in the Fourier transform, we are getting the signal, and what is the significance of getting this repeatedly?
I'm not sure what is whether you're asking what is the implication or why is it happening?
Significance, sir. Significance of
What is
discrete
its implication?
Significance of discrete
What is
time
its
Fourier
effect?
transform.
You're asking what is its effect?
Yes,
or
sir.
what is the reason?
The significance of doing it, sir. Discretization, discrete time Fourier transform.
Why we would do it? Need of this thing.
Need. Yes.
No. So we are not doing the Fourier transform. So if I look at only we don't need to do the Fourier transform. The Fourier transform is for the understanding. So let me show you now. So just look at the analog signal, which is the top graph. The digitized version looks fine, and the reconstructed version looks all right. Right? I mean, there are some very sharp corners, but I can do a better job than that if I want. Instead of using straight line connection of the dots, instead of joining all the dots by straight lines, I can draw a smooth line through that. That's what I mean by reconstruction. Now, if I reduce the sampling rate, sorry, what did I do? Sorry, my touchpad was acting up. So 65 hertz, 64 hertz of sampling, I'm able to get back the ECG signal more or less correctly. If I go to 32 hertz, I cannot get it back. You see, because if you look at the P, Q, R, S, T waves, I'm missing the Q wave here completely. I'm not able to sample it, right? So therefore, when I try to reconstruct it, I get this completely non-ECG like signal. So the question is, what should we do? Now, if I only look at my textbook and say you have to follow the Nyquist criterion, but what is the reason for the Nyquist criterion? That is what I'm trying to explain by showing the Fourier transform. The Nyquist criterion says that if your highest sampling rate is such that, let me run it, is such that you will not have interference between adjacent repeating blocks of the discrete Fourier transform, then you will be able to get back the original signal. I know this is not what the textbooks say, but this is another way of saying the same thing. Or another way of putting the Nyquist sampling criterion is to say that if you sample your analog signal at a sampling rate greater than the highest frequency contained in the signal, then you will be able to always get back the original signal. Okay, that's what I'm illustrating by showing the Fourier. Now, the reason I want to show this is I have another simulation somewhere which I will have to search for. But what I would suppose I have some noise here. Let's say I have 50 hertz noise. The 50 hertz noise will come up somewhere here. Okay. Now, I'm saying that a noiseless ECG, if I sample at 64 hertz, it is good enough. But when my noise comes somewhere here, it is outside my green rectangle. So the noise is also going to get aliased, and it will come in to into my green rectangle here, although it is outside. So what I should do before I sample, before I digitize, is make sure that all power above half my sampling rate is removed. That is what is called an anti-aliasing filter. Okay, I'll go on. Okay, so when we say analog filtering, I showed you these physical sensors and so on. They all have analog filters before they digitize. So your anti-aliasing filter has to be an analog filter. And analog filters can be low-pass filters, high-pass filters, band-pass filters, notch or band-stop filters. So I mentioned 50 hertz notch filters. That's also called a band-stop filter. I'll say a little bit more about this later. The filter order, people often talk about first-order filters, second-order filters, third-order filters, and so on. Now, all I'm going to say is, higher the order of the filter, better is the separation of the wanted signals and the unwanted signals. So if you can use a 8th order filter, then your separation of wanted and unwanted signals is going to be much better. But designing an 8th order filter is much more costly. Much more costly meaning the precision of the resistors, filters that you use will have to be of a very high precision. It'll have to be 0.1% and so on. And therefore, they have to be they will be much more costly. Now, why is it that they have to be so precise? Because if they are not precise, they will either give you the wrong filter effect, or it can even become unstable. Okay? Now, the simplest filters will only use resistors, capacitors, and if you like inductors. Active filters use uh, uh, electronics, that means active electronics, like operational amplifiers. So as an example, a second order filter will have two parameters to adjust, and you can think of those two parameters as the cutoff frequency as well as the cutoff sharpness. I'll say more about this later on. The so-called transfer function of a filter in general can be written as a ratio of two polynomials. Okay. So here I have a low-pass filter in the upper diagram and a high-pass filter in the lower diagram, and the transfer function of these two. These are using operational amplifier. These are the most common filters used. I also use them very commonly. Now, digital filters, once you have digitized it, all you have is a sequence of numbers. And the transfer function for a digital filter does not use Laplace transforms, it uses Z transform. And it is written like this. When you implement it, what you do is you calculate the present value in time of the output as a constant multiplied by the present value of the input plus another constant multiplied by the previous sample of the input, another constant multiplied by the the sample before that of the input, minus a constant multiplied by the previous value of the output, minus a constant multiplied by the preceding value of the output and so on. So this is a general form of the filter, and this equation can be obtained from the transfer function in a very straightforward manner. Now, it is common for digital filters to be designed starting from an analog filter. Why is that? Because we know that an analog filter is something that can exist in the physical world or the real world. And therefore, starting from an analog filter, if you design a digital filter, you know that it's a filter that can be implemented in real time. Again, I don't think I need to go into those details. I just want to mention it. So this is the equation that I have used for generating the ECG. So it might appear very similar to the equations that I wrote for the filters. So here, the output of at the present time depends on weighted sums of the output in the past. But here, I'm using only 4 outputs of the past, plus this Wn is white noise that is generated using just a random number generated in the computer. Okay. I think you are tired of looking at my face. So you can look at some of this. So you can look at your phones. So I started using this as a joke in my presentations. So you can look at your phones now, because usually in a lecture people will say, don't look at your phones. No? So now I'll give you a chance to look at your phones. So look at your phones and go to this website, 2k.xyz. You done that? If you want, you can go 2k.xyz/Suresh. It will take you directly to my page. If you want, I can. I'm sorry.
Got it, sir. Yeah.
I got it. Now go to the very first simulation, which is linear filters. Go to linear filters. That looks better on a laptop, but it's nice that it also runs on a phone. And if you click on a phone, I think at least on my phone, the EEG button, some of the text comes to the next line. So here there are 2 scroll bars. You can see you can adjust the EEG from alertness to relaxed condition. The top trace is the EEG signal itself. The second trace is the signal filtered, and you can adjust the cutoff frequency. I've called it the natural frequency, and you can adjust the sharpness of the cutoff, which I've called damping coefficient. So if I have a high cutoff frequency, you can see the input EEG and the output are more or less the same. Now, if I add noise, so in the second panel, in the control panel, I can add 50 hertz noise. So you can see there's a lot of noise. Can I do anything to remove the noise? Can I use a low pass filter? When I use a low pass filter, it looks like I can use a low pass filter to remove the noise. You can make this slower by changing the FPS. So I'll run it slowly on my screen. So it looks like I have cleaned it up just by using a low pass filter of 12.5 hertz. But I want you to think about this carefully. Suppose there is no noise and I'm using the same low pass filter. Here is the EEG in the top trace and the filtered EEG in the lower trace. Can you see the difference? You can also pause this if you like. Can you see the difference? So a lot of the rapid changes in the EEG have been removed because of the filtering. Can you notice it? You can see it on your own computer. And the waveforms will be different on every machine because there's a random number being generated. Okay? So it's not always a good idea to use a filter when you see the noise. You have to understand what the noise is. And instead of a low pass filter, let me use a notch filter and use a natural frequency of 50 hertz or a cutoff frequency of 50 hertz for the notch. Can you? So here I have the noisy EEG, which is very noisy. And now if I reduce the noise amplitude, you can see the output is not very bad compared to the input. So in this case, if I know that the noise is only 50 hertz, then using a notch filter is the best solution because it does not damage your signal. If you carelessly use a filter, you will also lose part of your signal. And for those of you who are interested, the frequency response of the filters that are being used are also shown if you scroll up. So this was the earlier filter, the low pass filter. The upper plot is the magnitude plot. These are Bode plots. That means they're drawn on logarithmic scales. The vertical axis is decibels in which is a logarithmic scale. Horizontal axis is also in a logarithmic scale because that is the convention. The lower plot, on my screen is the phase angle. And again, for those of you who are interested, these are the pole zero plots. And this is the impulse response. With this, I'll conclude. I hope you have fun playing the simulation.
Sir, Miss, this is very useful tool, and it's very
I hope so.
for all
Yeah.
of us. Means just to play around and understand the things by
Yes.
doing some. So it's a really very wonderful tool. So
So I wrote the linear filters some time back. The EEG I put in yesterday only for this lecture.
yes.
இது கான்ஃபரன்ஸ் ஒன்று கேட்டுட்டு நான் வந்துட்டே இருக்கேன் நான் வந்துட்டு இருக்கேன் I'm joining. I am aware of it.
Got to be muted, I think.
If you have any questions, please ask.
Yeah. So we are open for questions and answers from the audience, please.
Ma'am, I have one question.
Please.
Sir, actually, how we decide that which filters to be used for the processing? Because sometimes we work with the different projects, and sometimes EEG signal data is sometimes ECG signal data is. So as data is varying, range is varying, frequencies are varying. So how to decide which filters we should go for?
So you should first, if you have a good idea of the frequency in which the signal exists and the frequency in which the noise exists. So in the case of EEG, we know from EEG that has been collected and analyzed that the frequency band is somewhere between 0 hertz and about 30 hertz. And if the noise is only 50 hertz, we know that the EEG and the noise are well separated. So if we keep a low pass filter at about 40 hertz, but a very sharp filter, that means a high order filter, then we can cut off the noise. Or we can use a notch filter. In the case of an ECG, the ECG signal bandwidth goes from about 0.05 hertz to about 80 hertz or so. So if you have 50 hertz noise, the 50 hertz is right in the middle. So if you try to remove the 50 hertz, you are likely to remove some of the ECG signal itself. So in that case, if by chance you happen to know the amount of power in the ECG signal and the amount of power in the noise signal at 50 hertz, then you can design what is called an optimal filter or a Wiener filter. An optimal filter is a Wiener filter in this case. That means you cut off the noise without cutting off any of the, or you design the filter such that the attenuation at 50 hertz is in the ratio of the amount of power in the ECG to the amount of power in the noise. That's called an optimal filter.
Yes, sir. Yes. I got it, sir. Sir, one more thing. In majority of the research paper, they use in a sequence, low pass, high pass, and then notch filters generally.
Yes.
So, as they are referring, so we can also follow the same sequence for the EEG signals.
Yes,
Or
you can. Although it depends on certain situations. In some situations, the electrode polarization potential can be large. So if your polarization potential is, so for example, if you don't use very good electrodes, if you're in a hurry or the electrodes are put on by a patient or somebody at home, and they cannot place it very well, the polarization can be quite large on the order of 10 millivolts and so on. So then you have a large offset, and on top of this 10 millivolts, you have this 0.1 0.01 millivolt of EEG signal riding on it. Now, what if it is only a polarization potential? It is best to use a high pass filter first. So you remove the polarization potential, and then you can amplify it a little bit, apply the low pass filter, and then the notch. So it depends on the situation.
Yes, sir. Yes, thank you, sir. So one more question I have. Since we're talking about noise, and
Yes.
when we talk about EEG signal, there are two components that we are playing a role in EEG signal. That is artifact effects also, and the noise also. Many
Yes.
times we try to remove the artifacts also.
Yes.
So in this signal, how we can identify or distinguish, or some special filters we can use to eliminate that impact together?
Okay, let me put it like this. Let me call the artifact noise 1. Let me call what you are calling noise as noise 2. They're both noise. One is noise 1, noise 2.
Yes.
Now, what I mean by artifact is when I move my hand, there is some movement of the electrodes, and that results in an artifact. But and this noise 1 is a low frequency noise. That means it moves, it changes only at the speed that my hand moves, which may be on the order of, it may be on the order of, say, 1 cycle per second or so, 1 hertz or so, or less than that. My noise 2, which you have called noise, maybe 50 hertz noise, maybe some other random noise because some motor is running nearby, some fan is running, there is some switch mode power supply. All these are causing higher frequency noises. So if you, for the low frequency noise, your signal, let us say, is in the range from 0 hertz to 30 hertz, which is your EEG signal. Now, if you say, I don't mind losing some of the below 1 hertz part of my EEG signal, if I can remove noise 1, then I use a high pass filter that will remove noise 1, but keep my EEG only from 1 hertz to 30 hertz. And my noise 2, which happens to be greater than, let's say, 40-50 hertz, I use a low pass filter. So the high pass filter is for noise 1, low pass filter for noise 2.
Yes, sir, yes, got an idea. Thank you so much,
Okay.
sir. Thank you. It's a
Sure.
great session. Thank you.
Hello, sir.
Yes.
Yes, sir. I am Akanksha, sir. I have two questions. Sir, one question is, sir, you had mentioned that analog filtering is better than digitized filtering, as it take
It's
care of
better
noise
than.
at time of recording.
Yes, yes, correct.
So, sir, but like still, as during analysis, we prefer to use some bandpass filters in case some noise is still
Yes,
left.
yes.
So, what kind of filter is better in case of digitized uh,
See, I mean,
filtering? And
very often, if you have a pre-designed piece of hardware, you cannot change the hardware analog filters, the hardware filters.
yes, yes, sir.
Therefore, the hardware filters are fixed. They are
Yes, sir.
designed for what they will consider normal EEG or ECG.
Yes,
What I have found occasionally is a manufacturer uh, puts very harsh filters for things like ECG. So if they are selling ECG mostly to general practitioners, then the general practitioner is not too much interested in things like ST elevation, and QRS complex and things like that. They are mainly interested in few rough parameters and a printout that they can give to their patient. So many of these manufacturers simply use a high pass filter at 0.5 hertz and a low pass filter at about 40 hertz, which means as soon as you connect a patient to it, you get what looks like a fairly good ECG very quickly because you've got rid of the most common types of noise. But if you want to do a detailed analysis of the ECG, that is not good enough.
yes, sir.
So it's better that the manufacturer gives you as little filtering as possible uh, whenever there is doubt. So that later on, you can apply more digital filters.
Yes,
So
sir.
although
So,
I say that,
yes, sir. Sorry to
so it is very difficult to say it categorically that analog
interrupt.
filters are better in all situations or digital filters are better in all situations. You have to look at it situation based.
Yes, sir. So at time of considering, sir, in
Yes.
case of digitized filtering, which is the most preferable one or commonly used? Like Butterworth is there, so is that the one which is more standard, or can we use some
So
other filters which are better?
for if you are looking at a certain kinds of evoked potential analysis, mhm, where the time difference between peaks in the evoked potential is crucial. So
Yes, sir.
that if the time difference is very large, it may be a pathology. If the time difference is very small, it may be a different pathology. The in between is the normal signal.
Yes, sir.
Sorry. In that case, what is called preserving the phase of the signal is very important. So if you use filters that are not linear phase, then the time between the peaks can shift because of filtering.
Yes.
And in such situations, for a lot of biological filters, they use what are called Bessel filters. So in the case of the
Sorry, sir.
Bessel filter, Bessel, Bessel.
Okay.
So Bessel filters have a slightly lower damping compared to Butterworth filters. Slightly lower. But most people will not see the difference. Now with Chebyshev filters, you are likely to see some ringing. So people don't like to use Chebyshev filters for biological signals. But Butterworth is the
Mm.
most commonly used.
Okay. Thank you, sir. And
Okay.
sir, another question I had was at time of presentation, sir, you were saying something about the spacing between electrode positions and
Yes,
how it
yes.
impacts on the signal. So could you
Uh,
explain it again?
so if the spacing between the electrodes is larger, then the strength of the signal that you pick up is going to be stronger. But the strength of noise that you pick up from an external source is also going to be larger. So there is a kind of compromise.
So like what might be the ideal case of number of electrodes that you can see to take care of this noise and
In case of the EEG, it's better to go with the standard. The 1020 system is a standard.
Yes, so in 1020 also like there are 64, 128 channels and so on.
Yeah.
So like because even if it is 1020 system, the more the electrodes, still there might be more clustering.
So
and
technically, people use 128, 256, and so on. So there, the electronics. Two things. One, the electronics have to be much more precise because you're looking at signals that are smaller, and therefore they're more costly. And also because of that, they are only used in clinical situations in a hospital.
Thank you, sir.
Any other question from the audience? It seems there are no further questions. So,
Okay,
sir,
thank
basically, it is a really very insightful session, and the best part of the story is that you bring us down at such level so that you comes down to that level so that we all can understand you pretty well. So, the essence of this presentation today was that we all needed all those the very basic points which were somewhere missing in between. So it was really very helpful, sir, and you taught us
Thank
in a very effective manner, sir. So thank you very much for your time and effort, sir, and thank you for your guidance, sir.
Yeah, thank you.
Right, sir. Take care, sir.
Thank you. See you later.
Thank you, all of you. Thank you.
Thank you, everyone.
Thank you, sir.